Hello friends, I welcome you in lecture number 4 on partial derivatives. In this lecture we are going to discuss about chain rule. We will generalize chain rule from ordinary derivatives to the partial derivatives. So first we understand the chain rule for ordinary derivatives. So as we know, if y is a function of x and x is a function of t. So here y and x are both functions of one variable. So if y is a function of x and x is a function of t, then if we put value of x in y, we will have y as a function of t also. So y depends on t also. If value of x is put in this y equal to fx, then y becomes function of t also. So y is directly function of x and indirectly it is function of t. So if we want to find out derivative of y with respect to t, we have to apply chain rule. So we have to first differentiate y with respect to x, and in the product we will write derivative of x with respect to t. So this is chain rule for ordinary derivatives. If y is a function of t and if y is a function of x and x is a function of t, then derivative of y with respect to t is nothing but derivative of y with respect to x times derivative of x with respect to t. Now we generalize this for partial derivatives. Now suppose we have u as a function of v. U is a function of only one variable, and suppose v is a function of two variables, say x and y. Then because u is a function of v and v depends on x and y, u also depends on x and y. That means u is directly function of v, but indirectly u is function of x and y. So directly u is function of only one variable v, and indirectly u is function of two variables x and y. So if we want to find out partial derivatives of u with respect to x and y, we have to apply chain rule. So if we want to find out partial derivative of u with respect to x, first we will differentiate u with respect to v. So because u is function of v only, we write du by dv, that is ordinary derivative of u with respect to v, and in the product we will consider partial derivative of v with respect to x. Similarly, partial derivative of u with respect to y equal to derivative of u with respect to v into partial derivative of v with respect to y. So here u is function of v and v is function of x and y. So if we want to find out del u by del x, we will first differentiate u with respect to v, and in the product we will consider partial derivative of v with respect to x. Similarly, del u by del y is derivative of u with respect to v into derivative of v with respect to y. So we consider one example for this chain rule. Find partial derivatives of u with respect to x and y if u is given by this function sin of x upon 1 plus y. So we take this x upon 1 plus y equal to, suppose it is v, that is v is a function of x and y. So if we take v equal to x upon 1 plus y, u will be equal to sin v, and v is function of x and y. So if we want to find out del u by del x, we have to first differentiate u with respect to v, and in the product we will multiply with del v by del x. So by chain rule, del u by del x equal to du by dv, because u is directly function of v, into del v by del x. Now u is sin v, so du by dv is cos v, and del by del x of v is x upon 1 plus y, and here partial derivative is with respect to x, so we consider y as constant, that is 1 upon 1 plus y is constant, and derivative of x is 1. So we have cos v into 1 plus y, 1 upon 1 plus y, and we put value of v here. So we obtain del u by del x equal to cosine of x upon 1 plus y into 1 upon 1 plus y. Similarly, partial derivative of u with respect to y is, first we differentiate u with respect to v, because directly u is function of v and v is function of x and y. So del u by del y is derivative of u with respect to v into derivative of v with respect to y. Now u is sin v, so del u by del v is cos v, and del v by del y is nothing but partial derivative of x upon 1 plus y with respect to y. So here we will treat x as constant, and derivative of 1 upon 1 plus y is minus 1 over 1 plus y square, and we put v equal to x upon 1 plus y, we take negative sign here, and this is nothing but x upon 1 plus y square. So in this way we can use chain rule for partial derivatives to find out this type of derivatives. If we are comfortable, then we don't have to assume this v also. We can directly find out del u by del x as derivative of sine function is cosine of x upon 1 plus y into partial derivative of x upon 1 plus y with respect to x, which is 1 upon 1 plus y. So if we are comfortable, we can directly write down this derivative, but this is just to explain that how we are applying chain rule. Similarly, if u is function of v and v is function of 3 variables x, y and z, then if we put value of v in u, then u will also be function of 3 variables x, y and z. So we will have partial derivatives of u with respect to x, y, z, which we can find using chain rule. So if we want to find out del u by del x, first we differentiate u with respect to v, and in the product we have to write partial derivative of v with respect to x. Similarly, del u by del y is derivative of u with respect to v into derivative of v with respect to y, and del u by del z is derivative of u with respect to v into partial derivative of v with respect to z. So we consider one more example of this type. It is given that u equal to log of 10x plus 10y plus 10z, and we have to prove this equality. Sin 2x into del u by del x plus sin 2y into del u by del y plus sin 2z into del u by del z equal to 2. So here we will assume that suppose this is equal to v, so v becomes function of x, y, z and u becomes function of v. So we take v equal to 10x plus 10y plus 10z. So therefore u is log v and v becomes function of 3 variables x, y, z. So first we find out del u by del x. So by chain rule, del u by del x is nothing but derivative of u with respect to v into derivative of v with respect to x. Now u is log v and derivative of log v is 1 upon v, and del v by del x means derivative of v with respect to x, and because it is partial derivative we will consider y and z as constant. So derivative of 10y plus 10z is 0 and derivative of 10x is sec square x, and we put value of v here 10x plus 10y plus 10z. Now we have to multiply this del u by del x with sin 2x. So we multiply both sides by sin 2x. So here we have sin 2x into sec square x divided by 10x plus 10y plus 10z. Now sin 2x is nothing but 2 sin x into cos x, and sec square x is 1 upon cos square x. So here 1 cos x will cancel out, and we are having 2 sin x divided by cos x, which is 10x. So this is 2 10x plus 10x plus 10y plus 10z. Now here our function is log of 10x plus 10y plus 10z. Now if we interchange role of x, y, z, here u of x, y, z is this. Now if we interchange role of x, y, z, suppose we interchange x and y, then we have log of 10y plus 10x plus 10z, which is nothing but u of x, y, z. Similarly, if we interchange x and z, then we can observe that if we find out u of z by x, then also we will obtain this same function. So if we interchange, or if we replace x by y or y by x or x by z or z by x or y by z or z by y, function does not change. So that means this function is symmetrical function. So we can write down other two terms simply by replacing x by y and y by z. Here sin 2x into del u by del x equal to 2 10x divided by 10x plus 10y plus 10z. So if we want to write down sin 2y into del u by del y, if we have x here, here we have 2 10x. So by this symmetry, if we have sin 2y into del u by del y, here we will replace x by y. And if we want to write down sin 2z into del u by del z, here we will replace x by z. So here u is symmetrical in x, y and z. Therefore sin 2y into del u by del y is 2 times 10y divided by 10x plus 10y plus 10z. Here we have replaced x by y. Similarly, sin 2y into del u by del z will be 2 10z divided by 10x plus 10y plus 10z. And now we add equations 1, 2 and 3. So left hand side is sin 2x del u by del x plus sin 2y del u by del y plus sin 2z del u by del z. And in the right hand side we can see 1 upon 10x plus 10y plus 10z is common, and in the numerator we have 2 10x plus 2 10y plus 2 10z. And if we take 2 common here, 10x plus 10y plus 10z will cancel out, and we are having 2. So we consider one more example. It is given that u is a function of r, where r is given by this formula r square equal to x square plus y square. That is, u is a function of r and r is a function of two variables x and y. So we have to prove that del square u by del x square plus del square u by del y square equal to f double dash r plus f dash r divided by r. So this is also application of chain rule. Here u is directly function of r and r is function of x and y. Therefore u is indirectly function of two variables x and y. So we can talk about partial derivatives of u with respect to x and y. Now to find out second derivative of u with respect to x, first we have to find out first order partial derivative of u with respect to x. Now u is directly function of r. So first we have to differentiate u with respect to r, and it is ordinary derivative because u is function of only one variable r. And here we are differentiating with respect to x. So in the product we have to write partial derivative of r with respect to x. So we will require this partial derivative del r by del x. So that we first obtain using this formula of r square. So first we write down or we find out del r by del x before going for del u by del x. So here r square is x square plus y square. We are interested in del r by del x. So we differentiate this equation partially with respect to x. Now left hand side we will have, if we differentiate this equation partially with respect to x, then left hand side will be partial derivative of r square with respect to x. Now r square is function of r, but r is function of x and y. So here also we will apply chain rule. First we differentiate r square with respect to r into, in the product we will write del r by del x. So this is by chain rule. So derivative of r square with respect to r is 2r, and in the product we write del r by del x. And right hand side is derivative of x square is 2x and derivative of y square is 0, because we are differentiating partially with respect to x. Therefore y square becomes constant and its derivative is 0. So here 2 will cancel out and we obtain del r by del x equal to x divided by r. Now we find out del u by del x. So by chain rule, del u by del x is du by dr into del r by del x, because u is directly function of r. So first we differentiate u with respect to r, and in the product we write partial derivative of r with respect to x. Now we are not given the formula for u in terms of r. So u is arbitrary function of r. So we will write du by dr equal to f dash r, and value of del r by del x is x by r. So we have del u by del x equal to f dash r into x into 1 by r. So we are writing in this form because we require second order derivative of this product. So we will apply product rule. So now del square u by del x square is del by del x of del u by del x. We put this value here. Del u by del x is f dash r into x into 1 by r. Now here all these functions f dash r, x and 1 by r, they all depend on x, because r is function of x and y. F dash r will depend on x, x is already dependent on x, and 1 by r is also dependent on x. So here we have to apply product rule. Now we are having 3 functions, so we will take 2 functions as constant and we will differentiate third function, and that we will repeat for each function. So one function is constant and 2 functions are constants and derivative of one function. So there are 3 functions. So we have to differentiate all these 3 functions one by one, considering remaining 2 functions as constant. So first we consider these 2 functions as it is into partial derivative of 1 by r with respect to x. Then we consider f dash r 1 by r as it is and we differentiate x. And then we consider x in 1 by r as it is and we take derivative of f dash r. Now 1 by r, here also we have to apply chain rule, because 1 by r is function of r, but r is function of x and y. So here we have to first differentiate 1 by r with respect to r, and in the product we write down del r by del x. So derivative of 1 by r is minus 1 by r square into del r by del x. Now f dash r into 1 by r as it is, and derivative of x is 1, x by r as it is. Here also we have to apply chain rule. F dash r is function of r, but r is function of x and y. So first we write down derivative of f dash r with respect to r, and in the product we have to differentiate r with respect to x. So this is x by r. By chain rule, first we differentiate f dash r with respect to r, that is f double dash r into derivative of r with respect to x. Now del r by del x is x by r, so in the next step we put x by r in place of del r by del x. Here we take negative sign outside. This we can rewrite as f dash r into x divided by r square. Del r by del x is x by r plus f dash r divided by r, and here this we can rewrite as x by r f double dash r into x by r. So finally we obtain del square u by del x square equal to this. We rewrite all these terms. Here we have x square over r cube f dash r with negative sign. This is f dash r over r. Here x by r into x by r is x square by r square into f double dash r. Now here u is function of r and r is given in terms of x and y by this formula r square equal to x square plus y square. So here we can see r is symmetrical in x and y. If we interchange x and y in r does not change. That means r is symmetrical in x and y. That means u is also symmetrical in x and y. So we don't have to calculate second order partial derivative with respect to y. Because u is symmetrical in x and y, we can write down second order partial derivative with respect to y from this partial derivative with respect to x. So we will simply replace x by y in this partial derivative. So because u is symmetrical in x and y, we have del square u by del y square equal to, here x is replaced by y and this x is replaced by y. Other things remains as it is. So minus y square by r cube f dash r plus f dash r by r plus y square by r square into f double dash r. Now we add equations 1 and 2. So left hand side will be del square u by del x square plus del square u by del y square. And in equation 1 and 2, we can first add these two. So that will be 2 times f dash r by r. In this 2, we can write f dash r by r cube common. We can take negative sign also common. So we can write addition of these two as minus f dash r by r cube times x square plus y square. And in last terms, f double dash r by r square is common. In the bracket we will have x square plus y square. So that we have written here. Now we know that x square plus y square is r square. So in the next step we put x square plus y square equal to r square. So here r square will cancel out. Here also r square will cancel out. Here we will have minus f dash r by r plus 2 times f dash r by r plus f double dash r. Now this is nothing but 2 times f dash r by r minus f dash r by r, that is f dash r divided by r plus f double dash r. So this is what we exactly want as the addition of these two partial derivatives of second order. So in this way we can use chain rule to find out or to prove this type of problems. So this is all about today's session. I hope you like this lecture. Thank you very much.